Hello everyone, welcome back. In the last few weeks, we have understood how a MOSFET works. We have analyzed various situations and then we have developed, I believe, a good intuitive insight into how a MOSFET works. Today, I would like to uh, show you a glimpse of what is there in the most modern semiconductor devices that are being manufactured currently, right? So we have seen this graph already. We have seen how the technology nodes have been evolving. And whatever MOSFET theory that we developed, that is primarily applicable to the long channel MOSFET. And we have discussed the short channel corrections in the last lecture. So this is how a MOSFET at the end of the 20th century would look like. 130 nanometers is roughly where in 2000 we were there, right? So the MOSFET looks something like this, wherein this is a gate, and then there is an oxide in between here, and there's a channel. I mean, this is how physically a MOSFET looks like. This is what is known as an SEM picture, okay? Scanning electron micrograph, SEM, okay? So you can use electrons to take this image because it's a nanoscale device. You can't use a normal regular microscope. You need a special type of microscope called as scanning electron microscope, okay? So with that, you take an image and you can see the various structures. And there's a great amount of detail. And these edges that you're seeing are the source and the drains, okay? So this is how a MOSFET would have looked like at the end of the 20th century. And you need, of course, it would exhibit short channel effects, and then whatever we discuss is all applicable to this MOSFET. So what happened in the last 20 years? And this is usually not discussed in any textbooks. And I believe the textbooks are currently being rewritten. So to account for this, there has been a tremendous amount of progress. And it is my hope that I can give you some glimpse into that. So the material that I'm going to show you today is taken from various presentations, mainly by scientists at Intel at various conferences. So I would give you the reference to the conferences in the bottom. So if you're interested, you could always go back to those presentations. And I believe with the amount of knowledge that you have gained over semiconductor devices in this course, you will be able to understand what they're talking about. All right. So if you want to know the latest developments, you should go back and look at presentations at conferences. Okay. So yeah, in the last 20 years, a great number of technical challenges were overcome, and that has enabled us to continue the scaling process. And what are these? Okay. I'll only give you a glimpse of it. It is not my aim to discuss these things in great detail. It's probably, it should make you feel that, wow, okay, I didn't know that. That's the reaction I'm looking for. And I'm not really trying to explain that in depth what is happening. Okay, that would require an entirely different course altogether. Okay, so this was 130 nanometers, and this is 2000, right, at the turn of the century, and scientists were already realizing that the reason we were scaling oxide and scaling the transistor was to improve the drive currents. Okay, and of course pack in more transistors. But then at the turn of the century, already scientists realized that it is running into some problems because we could not scale. We supply voltages and mobilities were also getting affected. So they wanted to improve the drive currents, that is on current, right? And one of the great inventions that was deployed was to introduce what is known as strain transistors. Strain transistors was introduced in 2003. And what do we mean by strain? Well, essentially we have the regular MOSFET, and now on top of it, we understood that when we studied the basics of lattices and mobility and all that, we saw that the mobility of a semiconductor is dependent on the band structure, and band structure is influenced by the lattice spacing. So scientists wanted to increase the drive current in a transistor, and we know that drive current in a transistor is simply given by it's proportional to the mobility, right? We have seen the expression for it. And can we play around with the mobility? We can, of course, play around with VG and all that. But in addition, if somehow we can improve the mobility of intrinsic silicon, right, or silicon itself, right, that would be great. And a way to do that is actually to apply strain. Strain essentially means I apply a tensile strain, which means I stretch the lattice a little bit, or I apply a compressive strain, that means I compress the lattice a little bit. Let's say the lattice constant is 5.4 angstroms. I can stretch it and I can make it 5.5 angstroms. If I do that, I'm applying a tensile strain. And if I compress it, then I make my lattice constant 5.3, then I'm applying a compressive strain. So this can be done by incorporating some external materials. So in 2003, Intel introduced this idea of strained silicon. Of course, these were researched even before that, but 2003 was when they actually made it into the fabrication or the actual devices. Before that, there was of course a lot of research done by various researchers at universities and so on. Okay, so now how did they incorporate this tensile strain? They essentially deposited a silicon nitride capping film on top of the transistor, which caused the transistor to stretch a little bit, and that's why we show that NMOS transistor was actually having a strain which is stretched. The mobility was increased by that. And similarly, in PMOS transistor, they introduced silicon germanium source strains, which was actually causing the channel to get compressed, and that would increase the mobility again. So why and all that is, of course, you have to get into a lot of detail that you'll probably do if you're doing research. But for now, I just wanted to introduce that. Okay, there is this concept of strain. That means your lattice is being manipulated to improve the drain current. And this was done in 2003, and it worked, for a couple of years. So by 2005 already, they again make the transistor smaller. So this was the transistor which was looking in the 2003. And then by 2005, they had the second generation of strain technologies, and they managed to improve the drain currents further. But then a big challenge came up. And when we introduced the MOS capacitor, we talked about the oxide thickness, and we said that oxide thickness was actually coming down to nanometer scale. And that was a major problem. And one of the ways to overcome was that we have to introduce a high K metal gate, or rather high K dielectric. Okay, so this is what was done in 2007. So roughly, 13 years back. So this is basically in 1997. The silicon dioxide is basically substantially thick, and this is what is known as a TEM picture, transmission electron microscope, wherein you are shining electrons and then into the lattice and then seeing the transmission. And what you see here, the regular structure is all silicon, and this is silicon dioxide, which is amorphous, and then polysilicon or on the top. Okay, this is in 1997. The oxide was substantially thick, but by the time we came to 2005, it was like 0.8 nanometers. And because of that, there was a lot of quantum tunneling happening, which was increasing the leakage current, and that became impossible to live with. Okay. Then, of course, people knew that if you introduce high K dielectrics, we can increase the physical thickness of the oxide and thereby reduce the tunneling current. And finally, this was introduced in year 2007 when Intel introduced this high K metal gate, and they introduced this high K oxide. But then, if you introduce a high K dielectric, it was not enough to just introduce high K, because there were a lot of other electrical issues, and because of that, even the gate had to be replaced. So before 2007, the gate was polysilicon, but in 2007 it became metal gate. Okay, they had to replace both dielectric and the gate. So that's why this is called as high K metal gate process. This was in 2007, and this is less than 2007. Remember, originally in the 1960s and 70s, it was metal gate, but then we changed over to polysilicon gate for adjustment of the VT and so on, and also some lithography related issues. And finally, in 2007, we went back to the metal gate. Okay, and this was introduced to essentially restore that scaling of oxide. So you could continue to reduce the thickness of the dielectric and then increase the drive current. Okay, this was done in 2007. So we call these transistors as high K metal gate transistors, and this is 45 nanometer technology. So if you bought a computer, let's say around 2008 or so, you probably would have bought a computer with a high K metal gate. Okay. So this was okay. It worked. For again, one more generation, they managed to work. But then it eventually became, difficult to actually improve the drive currents any further. Okay. The reason was that if you look at the traditional technology, the ones that we have discussed so far, we call them as planar transistors. The reason they're called as planar transistors is that we are familiar with the structure of a transistor. It's just rotated. So basically, you have the source, you have the drain, and you have the substrate. Okay, and this is the field oxide that we talked about, or shallow trench isolation, whatever it is. Okay, it is the isolation between two transistors. So where is your channel length? Channel length is here. This is the length of the channel, and this is the width of the transistor. So you see that this is a gate, and under the gate you have an inversion channel that forms. Okay? This is the dielectric here shown in yellow, and below the dielectric is where you have a square of inversion layer, right? or a rectangular form. Just under the dielectric, you'll find the inversion layer. And essentially, all that current conduction is happening in the plane. That's why it's called as a planar transistor. And this is what was used till up to about 2011. But the challenge was that it was becoming increasingly difficult to control the gate, inversion charge with the gate voltage. So Intel came up with a very revolutionary technology. Of course, this was also studied for some time, but it was finally introduced in 2011. Okay, so the idea was that we will not have a planar technology anymore, but we will have a out of plane silicon. So now the silicon substrate is actually coming up like this as a thin slab. Okay, we call it a fin. Okay, now it's more popularly known as a fin. Fin essentially is this thin strip of silicon which is coming up, and then you surround that with a dielectric here. Now, this is yellow again, right? This is dielectric, and then surrounded with a gate. So now where will the channel form? The channel forms in the 3 dimensions. It will be in this line here. This is a channel under the oxide. There will be a piece of channel here, and then the piece of channel here, right? So this is the 3-dimensional transistor, or we call it tri-gate transistor. It effectively is like a 3 gates. No? So what will be the width of this device? If you think about it, if you relate it to the traditional width of transistor, what will it be? So we can clearly see that this is the length, right? Because the distance between the source and the drain, the silicon source is here, silicon drain is here. Of course, it is doped, right? It's not going to be the same, silicon. And under the channel, there is no doping. That's all there. So now, it's opposite doping, p-type doping, and then n plus source and drains. So this is the length. What will be the width of this transistor? The width will be, let's say this height of the fin is h. If I call this as height of the fin, h, and this is the width of the, this is thickness of the fin, t, the total width would be 2 times height plus the thickness of the fin, t fin, and h fin, right? So this is the width of the transistor. So you see what happened. We are able to make the dimensions smaller by introducing these fins. Because if you try to go smaller and smaller, there were a lot of practical challenges. So they could not make the transistors even smaller and smaller. So they went out of the plane into the 3rd dimension, and that is known as this FinFET or tri-gate transistor technology that Intel introduced in 2011. Okay, and of course there's a lot of detail, and if you go back and just look for this presentation, and you will find some details. And with your background in semiconductor devices, now you should be able to understand some of that. Okay, so now this is what it is. And the beautiful thing is, you don't need to have simple one fin. You can have more fins. So you can have multiple fins like this, and you can have an oxide like this. So that way, you are able to increase the width of your transistor. The physical area, lateral area is very small, but you can have much larger widths. Okay, so you know already what happens when you increase the width, right? I is proportional to the width of the transistor. So if you increase the width, you are increasing the drive current, on current of your transistor. And that's why you are actually able to charge your capacitor faster or discharge your capacitor faster. Okay? So you are actually improving the speed of your transistor. Okay? So this is what schematically it looks like. And practically, if you look at it, this is how the transistors look like. Just the gate, till up to the gate. Of course, there's going to be a lot of things on the top of it. But here, you see, these are the fins. These things are the fins of silicon. And across that, you have a gate. So if you look at this as one transistor, you can count how many fins are there. 1, 2, 3, 4, 5, 6. 6 fins are there. There's a certain height, there's a certain thickness. We can estimate what is the width. And of course, the gate length will be clearly whatever, this is the length of the transistor. Okay. So this is how Intel managed to do it in 2011. And we have the FinFET technology. Okay. It looks beautiful, but what is the exact benefit in terms of performance? That you can see in these graphs here. These are again taken from the same presentation by Intel. This is 22 nanometer technology. So in that planar gate transistor, we have seen this on-off ratios, right? We have talked about subthreshold currents. So this is, let's say, on current, ID versus VG. Okay, this is ID. So ID versus VG. So we know the on current to off current, right? I off this is. So if you look at the planar transistor, this is basically a comparison of 2 technologies, so planar and the tri-gate technologies. So they're normalized. So on current in this case is 1, the ion is 1. Off current is, let's say, 1 into 10 power minus 4, minus 4. So you have 4 orders of magnitude change in the planar technology. But we said that for good transistor for digital applications especially, you have to have higher ion to IOF ratio, right? This is 1 into 10 power 10. I'll just write 10 power 4. So you need to have higher ion to IOF ratio, and that was achieved by the tri-gate transistor or the FinFET. They called it tri-gate, but now we call it FinFET. Okay, you see there it's clearly, here the ion to IOF ratio is 10 power 5, 10 power minus 10 power 5 years, right? So that is a 10 times better transistor than the traditional planar gate. And why was this possible? Well, think about it. You are actually in a traditional MOSFET, you had the oxide, and below that you had the channel. So you're only using the gate to control the channel. But in a FinFET, you are actually having a gate which is surrounding the channel. So you have better electrostatic control on the channel. And that is why if you want to switch it on, of course, it will turn on. But when you want to switch it off, because you're electrostatically controlling it better, you have a lower leakage current. So this is in terms of the leakage current. And if we also studied this, in a very short time, we said that the time delay, right? The delay, we said, is proportional to C times V by I, right? The current. So if you increase the drive current, you're going to reduce the delay. If you reduce the voltage, you can also reduce the delay and also power dissipation, right? I mean, this is a very qualitative picture I'm giving you. So what happened is, we said that because of the threshold voltage, we could not reduce it further. We got sort of saturated, and we would like to reduce it further, but there was technological issues, as said. But with Intel's tri-gate technology, it turned out that they were actually, if you compare the delay versus the operating voltage, in a traditional technology, it was like this. Whereas if you go to a tri-gate technology, we are able to achieve much lower delays for a similar operating voltage. So in principle, you could also reduce operating voltage and still get the same amount of delay. So that is how Intel also managed to improve the performance of a transistor. This was in the year 2011, so 1 decade back. Okay, so all of these technologies were developed, within our lifetime, right? And of course, after that, what happened in the next 10 years? Well, the technology improved even further. We started out with the fin. If you look at this fin, that was a very nice picture, right? Looking, because it's taken at a low magnification. But if you go back and look at it closely, in 2011, the fins were of this shape. The height of the fin was not much, and then there's a surrounding gate. And over the next 10 years, this is 2018, I believe. 10 nanometers is about 2018. They managed to improve the height of the fin, right? And also the surrounding, gate. So basically, they managed to bring the fins closer and also increase the height of the fins. And by doing that, you are able to get a much higher performance of a transistor. And it might seem like, no, it seems easy enough, right? Just make it. But this is actually pushing the limits of technology. It took them 10 years to reach from 22 nanometers to 10 nanometers, or 8 years. The reason is you have to invent a lot of processes. These are done using very, very expensive equipment. If you look at the state-of-the-art semiconductors nowadays, the fabs that are required to fabricate it cost upward of $5 billion or $8 billion or so. So it's a lot of expensive equipment that is required to actually make them. Okay. So, but Intel has managed to do all of these improvements. Of course, after Intel, a lot of other companies have also done. AMD, Global Foundries, TSMC, and so on. A lot of companies have done these things. Okay. So these are the improvements that were done. Okay. And finally, what next? It's okay, right? I mean, we have understood at a high level, we understand what are the current technology. But now the race is on to develop the next generation of technologies. And what are they? Well, a lot of things are being discussed because all of these technologies have some basic limitations. Okay? So many things are being discussed. For example, we can introduce 3-5 semiconductors so that we can improve the performance. Or you can use nanowires as a transistor, right? Nanowire transistors. Or we have various other technologies that are being explored. We don't know what is going to work, but it is really the cutting edge of research right now. Okay. And I just wanted to show you the latest, last year in 2019, there was a paper by Intel where they showed, we have now seen that the fin has gone up, the transistor has gone out of plane now. But in addition, what they have done is an NMOS was fabricated like a FinFET, But then on top of it, you fabricate a PMOS structure, not next to it, but on top of it. That means you are actually further compressing the transistor, right? This is kind of a 3D stacking of transistors, which is what was done by Intel here. Okay, they demonstrated this in 2019. Okay, so there is a lot of progress that is happening, and yeah, my effort was that basically we want to uh, give you a glimpse of it, okay, beyond the textbooks. Okay, so and what else? Okay, so in the end, I would like to stop with this slide. This is what I have shown in the introduction. And so this is the exponential increase in the computational capacity over the last century, right? So, and especially in the last 50, 70 years, so starting with 1948, year 1948, sorry, starting with 1948, we had about, one computation per dollar per second, I said. Now, with the increase in these various processes, we have managed to increase this. And now we have come close to 2020, somewhere here, we are there. What next? There are a whole range of ideas that are being discussed, and no one really knows what. We believe that optical technologies might play a crucial role because optical technologies are inherently have higher bandwidth and they actually can go faster. That could be one potential direction. You bring an optical interconnect onto a chip, or we bring in quantum computing, which is a completely different paradigm altogether. And if it really works out in the field, it will change technology. You can't even imagine what it can do right now. Just like somebody, if he was there in 1950s, they could not have imagined what MOSFETs would have done in the last 70 years. Similarly, if quantum technology really is practical, we manage to implement it and actually at a cost-effective level, then it will change the world. Okay, so and or it could be based on biosystems, using something called as neuromorphic, similar to neuromorphic biosystem, neuromorphic computing, and things like that. There are various things that are being discussed in the scientific community, and uh, it's been my effort to show you a glimpse of that. The reason is, if you want to work at the cutting edge, we need our youngsters to be educated in these things. Okay, so that's been the effort, and you are welcome to explore some of these things further, and I'm sure you'll find it fascinating. Okay, with that, I will stop my discussion on the MOSFETs part of the course. In the next 2 weeks, I'll discuss optoelectronic devices, which is another fascinating dimension. All right. So with that, I'll stop. Thank you for your attention, and we'll see you next week. Have a great week. Bye.